I'm Rabin Adhikari. The original topic of my presentation was neural networks, but this topic, introduction to deep learning, I thought this was more suitable for this class. So I would like to give on this topic. So let's start the presentation.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things. So, for instance, they could have me say things like, I don't know, Killmonger was right, or Ben Carson is in the sunken place, or, how about this, simply, President Trump is a total and complete dipshit. Now, you see, I would never say these things, at least not in a public address, but someone else would. Someone like Jordan Peele. This is a dangerous time. Moving forward, we need to be more vigilant with what we trust from the internet. It's a time when we need to rely on trusted news sources. It may sound basic, but how we move forward, the age of information, is going to be the difference between whether we survive or whether we become some kind of fucked up dystopia. Thank you. Stay woke, bitches.
So let's start. As you have seen in the video, that is the power of deep learning and what we can do using deep learning. And I'm not going to talk about the ethics behind it, but what a brief introduction to what is deep learning. So let's start with what deep learning really is. So as we can see from the diagram that I have seamlessly copied from a source in the internet. Mm, so the artificial intelligence started way ahead in 90s, 50s, 70s, and there was the uh, technique that enables computers to mimic human behavior. And later on in the 1980s, the machine learning came into bloom, and it was really just the ability to learn without being explicitly programmed. The AI basically used rule-based methods too, but machine learning is not exactly about rule-based methods. And a little bit later on in 2010s, or we can say just a decade earlier, we had deep learning, and it automatically extracted the patterns using neural networks. And we needed a little bit less feature engineering than the machine learning. So we can say that machine learning is a part of AI and deep learning is a part of machine learning, like subset. So why deep learning and why now? So as we can see here, uh, slide here. Yeah. Mm, it started in 90s, 1940. The as we can see the deep learning timeline, and we are pretty much uh, the current state in neural network, like pre-training in 2010. And but why is it blooming in the current decade? Let's talk about that. Sorry, I had the slide in latter part. So why deep learning? The hand engineered features are time consuming and not scalable in practice. So this is the basic fundamental difference between machine learning and deep learning. And how can we learn the underlying feature from the data if we are not hand engineering the features ourselves? So these are the features of what a CNN learns from the data at different levels. So if if we talk about the history, we can see that we basically hand engineered the edge detection filters, and then after we selected the landmarks, facial landmarks, and then we uh, put some kind of classifier to reconstruct the faces or recognize the faces from the those face landmarks, and these were the hand engineer features. But as we can see that the CNN launch, CNN is a type of neural network, convolutional neural network, which launched these kind of features by themselves, and we do not need to hand engineer them, and we have an end-to-end pipeline which can recognize the different objects like faces, cars, elephants, and chairs in the objects in the images. So why now? Mm, Pretty much everyone in this class has taken big data in our second elective, so uh, I think they have uh, understanding why we need the deep learning, and why the demand of deep learning and is blooming now. It's because of the larger data sets, and data is coming from everywhere. Every sensor is giving us data, and we can train a model or analyze the data using the deep learning methods. And the second second point is hardware, and we can I have not shown you the uh, graph how the hardware is scaling by every year. So we have uh, but we you have an idea how GPUs are become massively bigger and bigger every year. And as you know already know that GPU has many cores, and those cores make the matrix multiplication um, massively parallelizable. And another one is software. We have improved techniques, new models. Every model is coming uh, every day in the conferences and journals. So tools like PyTorch and deep learning has improved our current state of the art every day. So let's start by going into a building block of deep learning, the perceptron. It's like a Lego block of a neural network. So let's go into the forward propagation. And forward propagation is just what I have shown you right now is a perceptron is a linear combination of the inputs. Uh, so we have weighted the inputs xi with wi with a bias w0, and we have added an non-linear activation function on top of it. So we will let us see on what the nonlinear activation function does to the output. But basically, what's happening here is a affine transformation, or we can basically say the linear transformation by a bias, and which is passed into a nonlinear activation function. So basically, we as seen a linear algebra classes can easily recognize, we can modify this upper equation to the lower one, which is basically a inner product of the x1, xi, and wi. This can help us parallelize in the GPUs, and matrix multiplication is definitely faster than a for loop. So So common activation function. What really the G of here, what this function really is given by these common knowns, and there are definitely many other activation functions which I have not included here. But if you at least if you have an idea, these three should be the ones you know. So first one is sigmoid activation function, hyperbolic tangent, and ReLU. So I'm not going to bore you all about these activation function and their gradient, but what we can see here is sigmoid has its output input. All of them have an input range of minus infinity to infinity, but the output range of sigmoid is 0 to 1. So what else aligns with 0 to 1? So we can easily see, if you think of a probabilistic way, we can easily see that this can be used to model a probabilistic function. So sigmoid is usually, it was used in the earliest in the previous in the past, but nowadays definitely we can see that sigmoid is used in the latter layers or the final layers to change the weights into probabilities. So, and the hyperbolic tangent is used to convert this minus infinity infinity to minus 1 to 1 range. So it can be like if you have generated the image, it can be say to generate from minus 1 to 1. Oh, you can it is also used in LSTM like networks in the middle layers too. So on what is ReLU? ReLU is a basically it's a linear unit which is rectified. So what is rectification? Rectification is a conversion of a negative value to a non-negative value. So it is converted. Our range of minus infinity infinity is converted into a range of 0 to infinite. So basically, is a maximum of 0 to z. Either is it a positive value or it is a z. It is z. So oh sorry, either it is z or it is a. It means it gives a non-negative value. So what is the importance of activation functions? So the purpose of the activation function is used to introduce the non-linearities into a network. Uh, Although you can see that it's a linear unit, but it is not exactly a linear unit because the negative values are uh, turned into zero. So, and so these non-linear activation functions produce a non-linear uh, decision boundaries. So non-linear activation function, as you can see in the left figure, it produces a linear decision. No matter how big the network is, how much we stack the network, it will always produce a linear activation function. But if we go on stacking a non-linear networks, we can uh, easily approximate a complex function. So let's go into building a neural network with perceptrons. So this is a multi-output perceptron. Um, the index shows zi is for the first node and sorry, z1 is for the first node and z2 is for the second node. So the same equation as earlier is combined into a single one to form to give an index. So basically multi-output perceptron is a network that has a multiple output like the perceptron we have seen earlier. So this is a single layer neural network. Actually, we can see there are three layers: input layer, hidden layer, and an output layer. But usually in neural network terms, we always determine the number of layers by the intermediate hidden layers only. So there are only one hidden layer. Obviously, every network has an input and output layer, so we only count the hidden layer. So this is a single layer neural network. So we can see that this is the equation for the single layer neural network, and there is an additional index in the superscript, and this is to denote for the yi part. So sorry, for which layer. So this is for the w1 and this was w. So these are the words for the first superscript, and this is for the second superscript. So basically we are combining the previous equation into one. So this is the deep neural network. If we go on stacking the hidden layers, it will form like this. And this is sort of just a short form representation of the initial one. There will be a big messy on the screen. So I have shown the little boxes in there. A kind of disclaimer, this is not my slides actually. Because I took a very much chunk of the slides from the MIT Introduction to Deep Learning course. So slide credit goes to that course. Basically, it was Alexander's slide. So how do we apply neural networks? Let's see a problem, example problem. Will I pass this class? Will I pass this class? So uh, we have two features: the number of lectures we have attended and the number of hours spent on the final project, if we have one. Uh, so these are the past data sets, data points. These green ones are the ones that people have passed, and red ones are the failed. So if we see a point here, we can easily guess. Basically, the person will have a great chance to pass actually. So we need to predict. We need to make the neural network predict that the person will pass with a certain probability. So if we have a untrained neural network, if you pass the 4 5 point of here to the neural network, we can see that the untrained neural network predicted 0.1. But actually, we can easily see that it's need to be about one. It will definitely not be one because it is the sigma is asymptotical to one, but it needs to be near to one. So here comes the loss. The loss, and so it needs to predict one, but it predicted 0.1. So this difference between this distance between the predicted and actual value is the loss function for the neural network. We have varying definitions of what actually the distance is. So we can say that distance is similar to loss. Uh, so what empirical? So this is a loss for a single point. And what is a empirical loss? The empirical loss is the loss over an entire data set. It is also known as objective function, cost function, or empirical risk. So if you pass this data, and this predicts this fx or y hat, and this y should be the actual answers to the answer that neural network should have provided, and this loss averaged over all these points and gives us the cost function or the empirical loss. So as I have said earlier, what actually the distance is. If you know that distance doesn't always mean a Euclidean distance. So what actually a distance means is means the example of some distances or the loss is binary. The first one is binary cross intrabilus, and it can be used to use for the models that output a probability between 0 and 1. And we do have different models that do not predict between 0 and 1, like a regression problem. So basically, we are talking about classification right now. So this is the one. This is the loss. If we can see that the actual output is either 0 or 1, so this is just a combined form for 0 and 1. It is only activate the uh, actually only one part is non-zero at a time. So either it is this log or this is this one log. So log is just a decreasing function. So if values will be predicted 1 and it is predicted far from 1 towards 0, it will penalize it. And if it has to be predicted 0 and it's predicted towards 1, it penalizes it. So if you have known the cost interval from Shannon's theorem, it is just the cost interval minus y, the log probability of y. So another one is mean squared loss. It is basically used most of the time used in regression models. We do have other losses, but we will not talk about them. Just mean squared loss is so just the difference between the actual and predicted, and squared is just squaring, and mean means taking the mean over the whole data set. So basically, it's the sum of square of residues. If you have known about the regression problem, so it can be used to predict the final grades, and not actually if you pass or not. So how do we actually train neural networks? So we have to optimize our loss function. So let's see how see what this equation has to say to us first. This is the loss function, and we have to find a value w asterisk that has a minimum value for this loss. So what this equation actually says is that we have to minimize this loss, and the given argmin, the given value of w that minimizes this loss is to be assigned to w asterisk. This is our optimum point of loss. We need to find a point where the loss is minimum among all the combination of the entire this landscape of weights. So we need to achieve the lowest loss, and what this W really means is W0, W1 for each layer. So we can do this using a gradient descent. So how gradient descent really works is we randomly pick a initial point at W0 and W1. What I have shown here is just a two-dimensional, just a three-dimensional landscape. So we actually have only two words, just a simple linear problem here. For us, in just as two words, we have seen the landscape is pretty much hard for for the gradient descent to converge directly. So this can be scaled to a bigger landscapes that I have a picture for you at the end of my slide. So this goes on being bigger and bigger and harder problems. So for the sake of visibility and understanding, I have only showed you only two words. This can be scaled to a higher number of words too. So let's pick number of, and pick a random point for which this is just a contour plot. So and the red region shows a higher loss and the blue region shows a lower loss. So as we can see that if you pick a random initial point, it should lie between the global maxima and the global minima should lie. So first we compute the gradient of the point. um, with we should compare the gradient at that point with respect to the loss function. So after computing the gradient, we can see the gradient points the direction of the highest ascent. So ascent. So we have to minimize this loss. So we have to descend from that point. So we take a small direction in the opposite direction. Sorry, small step in the opposite direction. So we go on taking the small steps until we reach convergence. If we have a plot right here, we can see that this is the global minima, but uh, we do not always have a notion that if we have reached a global minima or not. So we have to repeat until a convergence occurs. So this may be a local minima or a global minima. You never know. So actually, that the same slides are combined. If we combine the same slides into a single algorithms, this is the algorithm you get. So this is basically a probabilistic way of saying that you have to initialize randomly with a mean of zero and standard deviation sigma, and loop until there is no change in the words by taking small steps in the opposite direction of the gradient, and that converged weight is our final weights. And so how do we calculate the weights? So uh, we are using the chain rule here. So we have got just a loss in the final layer, but we do not have exactly a loss in the middle layer. We just apply the same rule by calculating the gradient of this cost function with respect to y and yi, and with respect to w2, sorry, y hat, and with respect to w2 is just the derivative of y hat with respect to w2. But if we need to go backwards in the neural network, we have to apply more and more chain rules for every weight using gradient from the lateral layers. So this is the fundamental theme of the backpropagation introduced by Jeffrey Hinton. So as I have told you earlier, this is the lost landscape, and this is it is hard to find. Actually,